Okay, here we go. So this is part one of the chemistry midterm exam review. Counting significant figures. The key is if there is a decimal point anywhere in the number, then you do not count any zeros to the left of the first digit. So in these numbers, we're going to cross out the zeros on the left. This first one doesn't have any zeros on the left, so that means we're going to count all of the other digits. So that's 3 digits. That has 3 significant figures. This one over here has 3 significant figures. The 0 on the right in both of these count because there's a decimal point. So this one also has 3. This one down here has 2, just the 1 and the 7. If there's no decimal point, like there isn't in this one, or this one, or this one, then you don't count any zeros on the right. So that's a 0 on the right for that number 6 there. There are 3 zeros on the right for number 3. So we cross out any zeros that are to the right of the number if there's no decimal point, which only leaves 2 significant figures there. It leaves 3 here. All 4 of the digits in this number count. That 0 is in between 2 other numbers, which is why it counts. Converting into scientific notation. So we start in the first one with a decimal point that's here, even though it's not written. And in order to get to scientific notation, you have to have a digit, a number between 1 and 10. So in order to do that, I have to move this decimal point 1, 2, 3, 4, 5, 6, 7 times to the left. And what that leaves me with is 4.7 as my number between 1 and 10. And then the second half is always times 10. And the power of 10 that we're going to use is the number of times I had to move the decimal point altogether. Not just the number of zeros I had to get past, but it also includes that 7 that I had to move by. So in that case, there's 1, 2, 3, 4, 5, 6 zeros plus the 7. I moved 7 times. So 4.7 times 10 to the 7th power. Since this is a big number, it's a positive exponent, so it's positive 7, 10 to the positive 7th. In number 14 here, I have to move 1, 2, 3 zeros, and I also have to get past that 3. So I moved 4 times. I've got 3.71 times 10. I moved 4 times, but I moved 4 times to the right. It's a small number, so I have a negative exponent. So 3.71 times 10 to the negative 4th. Now, if I'm converting from scientific notation, then the exponent tells me how many places I have to move that decimal. Since this is 10 to the 5th power, it's 10 times 10 times 10 times 10 times 10, then you know that's going to be a big number. So I'm going to have to move that decimal point over to the right, 4.12, that's moving it twice, and I have to move it 3, 4, 5 times. So the number is 412,000. Number 16, I'm moving 3 times, that's what the 3 means, but it's a negative 3, which means I had a small number. So I'm going to move 1, 2, 3 times to the left. And that leaves me with 0.00201. Okay, the number of protons, neutrons, and electrons for these atoms. If a charge is not listed, assume it's neutral. So for the first one, there's no charge on it. So we're going to assume it's neutral, which means that the number on the bottom, and this part's always true, the number on the bottom in this type of notation, and normally it wouldn't have the line there, that's just a formatting thing, but the number on the bottom in this notation is the number of protons. So there are 29 protons in that atom. Since it's neutral, that means it's also the number of electrons, 29. And the number of neutrons, we find it by taking this top number here. The top number is the mass, which is the protons plus the neutrons, which means if there are 29 protons and the total is 63, that means there are 34 neutrons, because 29 plus 34 is 63. In the next one, the bottom number, 26, still the number of protons. That's always going to be true. The number of electrons, though, is different because this one has a charge of plus 3. A charge of plus 3 means there are 3 fewer electrons than there should be in a neutral atom. So I'm going to take away 3, and we'll say that there are 23 electrons. The number of neutrons is 55 minus 26, which is 29 neutrons. And then down here, the way these are written, bromine tells you the element. You can look that up on the periodic table to find its atomic number, which will tell you the number of protons, which in this case is 35. That's what you're going to find on the periodic table for bromine. The 79, bromine 79, that 79 number is the mass, so we're going to use that to find the neutrons in a second. It's neutral, so the electrons are 35 just like the protons, and then the neutrons are 79 minus 35, which is 44. Uranium 235. If you look up uranium on the periodic table, it's element number 92, which means it has 92 protons. It's neutral, which means it also has 92 electrons. And the number of neutrons is 235 minus 92, and that's going to be 143 neutrons. Last one, it's nitrogen, which is atomic number 7, so 7 protons. The electrons, it's got a -3 charge. Negative charge means there's extra electrons, and in this case there are 3 extra electrons, so a total of 10, because a neutral atom would have 7. So every time you add a negative onto an ion, it means you're adding an electron. So 7 protons, 10 electrons. Overall, it's a charge of -3. And then the number of neutrons is 15 minus 7, which is 8. Okay, the average atomic mass of chlorine given here. The two isotopes are chlorine 35 and chlorine 37. Which one would we assume is more common? The thing you have to keep in mind here is that this average atomic mass is not a straight average, because if you add 35 and 37, divide by 2, you'd get 36 exactly. The fact that it's 35.45 instead of 36 is because we take into account, when we do this weighted average, that one isotope is more common than the other. So we sort of shift the average toward the more common isotope. So when you have a problem like this, what you have to look at is which isotope is the average closest to. In this case, it's closer to 35 than 37. So Cl35 must be the more common isotope. So, and then if you look at the next one, we're actually going to try to calculate the average atomic mass. The isotopes are 20, 21, and 22 down here. And we're given these percentages. These percentages represent how common each isotope is. So as you can see, most of 90% of the neon atoms in the universe have a mass of 20. So we call them neon 20. That's the biggest number. That's the most common isotope. The other two are less common. Neon 21 is very rare, less than 1%. Neon 22 is a little less than 10%. So when we do the average, we're going to take into account the most common isotope of neon 20, and we're going to sort of favor that mass. Because if you just add 20, 21, 22, divide by 3, you'd get 21. But that's not what we're going to get. So in these cases, what you're going to do is you're going to multiply the mass number times the percent and divide by 100. When you do that for the first one, you get 18.096. You do it for the second one, 21 times 0.27 divided by 100 is 0.0567. And for the last one, 22 times 9.25 divided by 100 is 2.035. When you add that up, you get 20.1877. We're going to round off to 2 decimal places, which would give us 20.19 atomic mass units. So you can see the average is very close to the most common isotope, and that's how we work that out. Nuclear equations. So what we're really doing is we're filling in the blanks in these equations, and you do that by remembering that it's an equation. So these arrows are kind of like equal signs, which means that all the numbers on the top and the bottom have to add up to the same total on both sides. So in the first one, we have uranium-238. Mass is 238. Atomic number of protons is 92. And then on the right, we have this 42He, which could also be written as 42 alpha. It's a really bad alpha, but it would look sort of like that. But the point is, there's a 4 on the top and a 2 on the bottom, and then there's this blank over here that we need to fill in. So the way we fill it in is we say, okay, we started with 238 on the top left. On the right so far, we have 4. So what's the difference? Well, the difference that's still sort of missing is 234. And on the bottom, we had 92 on the left. So far, we have accounted for 2 on the right. So what's left? 90. And then you have to look up element number 90 on the periodic table, which would be thorium. So thorium-234 is the missing piece there. In the next one, the number on the top actually doesn't change, which means the number on the top of the missing piece is going to be a 0 because there's been no change. On the bottom, the number actually is less on the left than it is on the right. It goes from 19 to 20. So the thing that you have to add to 20 to get 19 is a -1. So that's the number that goes on the bottom. And whenever you have a 0 on the top and a number on the bottom, you can put a little e there because it's either a beta particle, which is an electron, or if it's 0 over +1, that's called a positron, but we kind of write them the same way. 0 over either plus or minus 1 and e. All right, in the next one, we have 59 and 1 on the left, and we have 0 so far on the right, which means in order for the numbers to be the same, the missing number here is 60, 59 plus 1. And then we have 27 and 0 on the right, and we have so far -1 on the left. So the number that's missing is 28, because 28 plus -1 is 27. And if you look up element number 28, it is nickel. So nickel 60 is the missing piece. All right, the next one, now we have the blank here on the left. So we've got on the right 239 plus 4. Well, 239 plus 4 is 243. And then 95 plus 2 is 97. So we look up element number 97, and that is berkelium, Bk. And again, here we have the blank on the left in this last one here. So we've got 9 on the left, and we've got 12 on the right. So that means we're missing 3 from the left for the top. And then we've got 4 on the left, and we've got a 6 and a -1 on the right. 6 and -1 is 5, which means on the left we have 4. So we got to put a 1 down here. Atomic number 1 is helium, so we put an H there. So those are all the missing pieces, and again, you find those by figuring out how to get the numbers on the top and the numbers on the bottom the same totals on both sides. And you do whatever you have to do to get from one to the other. Okay, a couple of half-life questions, and then that's the end of part 1. So the radioactive half-life is 22 years. If you started with 1,000 grams now, how long will it take you to have 125 grams? Well, there's a couple of different ways you can do this. The simplest, I think, way to do it is to say, all right, if I started with 1,000 grams, a half-life means you cut the starting amount in half. So after 22 years, I would have 500 grams. Right, so you start at 0, right, today, and then wait 22 years, you'd have 500. If I waited another 22 years for a total of 44 years, I'd have 250, right, because you cut the number in half. And then after another 22 years, I'd have 125, so that's a total, 3 half-lives is 66 years. So after the first 22, it goes down to 500, the next 22, it goes down to 250, And then the last 22, it goes down to 125, which is what we said we wanted up here. So the total time that goes by is 66 years. And the second problem is similar, just sort of has a little different part at the end. But the way we're going to solve it is going to be basically the same. We start with 400 grams, according to the problem, and we end up with 25 grams. Well, how long does that take? Well, let's see, I got to cut it in half. 200, cut that in half, that's 100. Cut that in half, it's 50. Cut that in half, it's 25. So how many times did I have to cut it in half? Well, I cut it in half once. Right, start with 0. Cut it in half once, twice, 3 times, 4 times. So 4 half-lives had to go by to get from 400 down to 25. And according to the problem, that was 148 seconds. So if 148 seconds is 4 half-lives, then 1 half-life is 148 divided by 4, right, which is 37 seconds. Okay, so 37 seconds would be the first half-life. So the first half-life goes from 0 time to 37 seconds, and then add another 37, it goes to 74. Another 37 seconds is 111 seconds, and then another 37 seconds gets you to the 148. So that's the total. So that's the end of part 1. The next part is going to start with electron configurations, so we'll take that up on part 2.